Good afternoon, everybody. Welcome to another exciting afternoon of Chem 170 Organic Chemistry with your host, me, Dr. White. Now, a couple things upcoming. A week from this Wednesday will be test number 3, and it will cover carboxylic acids and their derivatives and amines and their derivatives. And by the end of the day, I'll be through with all the material, actually before the end of the day, that will be on test number 3. And test number 3 will be similar to test number 2 in the sense that we'll have a similar point breakdown. There'll be general knowledge, then there'll be nomenclature, and finally reactions. And similar to test number 2, test number 3 will have 3 or 4 synthesis problems. If I put any more in, that'd be cruel, unusual punishment, which I think is still outlawed by the Supreme Court, but I don't know, but I won't do it. So that's coming attractions. Don't forget to be handing in your lab this Wednesday, as we did last Wednesday. And with that, let's get to work. Now, on last Wednesday, I went through and did examples of this reaction. Remember, this is an amide, and if you react it with sodium hydroxide and water, what do you get? You get the carboxylate anion of the carboxylic acid you would have used to make that amide, plus the amine you would have used to make that amide. Remember, R prime and R double prime can be hydrogen. Now, before we go any further, there's something I forgot to do. Uh-oh. Did any of you happen to pick up a bottle of vinegar and say, oh, it contains acetic acid, and that's a carboxylic acid? Did you? Did anybody happen to pick up a bottle of ketchup, see it contains vinegar, which contains acetic acid, which is a carboxylic acid? Or did you pick up a bottle of nail polish remover and see it had ethyl acetate, which is a common name for an ester that's in that product? Or did you happen to do your laundry and use a fabric softener and consider it's got a quaternary ammonium salt in it? Did you do that? Did you have real hot peppers and all of a sudden, wow, that's hot? And say, oh, I know what's making it hot. It's an amide, capsaicin. Remember, organic chemistry is all around you, and it won't hurt to think about it outside my class. And one more thing I haven't done, and I should have, we're doing quaternary ammonium salts. Now, before the pandemic, they were in stores. And now, since the pandemic, they're still in there, and they're actually in a lot of classrooms. I haven't been to ECC in almost 2.5 years, but I know they had them before we left. I teach at College of DuPage, they've got them. Now, there are 2 types. One has bleach, sodium perchlorate, and the others, which you get at the supermarket, which work just as good under these conditions, have a quaternary ammonium salt. And let's take a look at this. And I don't see the ingredients, but if you look on here, it's hidden right here. You can see the name of different quaternary ammonium salts right here. It's there, I looked, you can't see it real well. But these disinfecting wipes, most of them that you get at a supermarket or anywhere contain a quaternary ammonium salt, because certain quaternary ammonium salts, not the one used for fabric softener, will kill certain things like bacteria and viruses even. So they're good things. Now, time for Dr. White to gross you out. Many years ago, I don't know where I saw it, and I didn't keep a copy of it. Somebody did a really interesting study. They took swabs from various areas like handles and also the place where a child sits in a supermarket cart. And they analyzed it. And they found about 75, 80% had fecal material they could identify. Ugh. So ever since I have seen that study, whenever I go into a supermarket or anywhere that has a shopping cart, the first thing I do is get one of those wipes and wipe the bars and the place where if you had a kid, you would sit your child and make sure they're clean. Because I know what could be on there. Kind of like that. But anyways, back to chemistry. All right, I have a very important announcement. Hold on, let's make it super important. Important announcement time. Ooh, Manching whistle on top. But anyways, as of now, I will not cover any new general reactions. As of now, I will not cover any new general reactions, but the rest of the semester, the reactions you've already learned, we're going to take it out into the real world and see where they're useful. Now it gets exciting. There will be one general reaction that I'll show you a slight wrinkle to it, if that's the right term, wrinkle, but that I didn't teach you when we went through it in ketones and aldehydes. So it's sort of new, but it's not sort of new. But that means no new general reactions for you to memorize, except the ones for test number 3 if you haven't. And I thought I'd give you that. And on Wednesday, I'll have another big announcement that you will like. All right. The next slides, I'm turning the switch. We'll just be on a test to the off position for a while. But I just want to talk about some things that are in our daily life. Now, this is called we're going to talk about aromatic diazonium compounds. This functional group is called an azo group. Benzene ring, 2 nitrogens bond together, they have a plus charge, and you have an anion, it's usually chloride. And these are very important. You say it about everything. How is it important? You see, I even put on there, note, this will not be on the test. If you take an diazo compound and react it with a phenolic compound, a benzene ring with a hydroxyl group, alcohol on it, you have what's known as a coupling reaction. And you get this new molecule, which this is called an azo functional group. And these are called azo dyes. Since the late 1800s, early 1900s, all the clothing you buy that's not pure white, it has a dye, a color to it, is due to these dyes. Now, if you put nitro groups and other things on the benzene ring, you get different color dyes. And these are used like the top I'm wearing to make it this color. Now, if you go back to the Roman times or after that, the Middle Ages, they didn't have this. So how did they get a dye? They've got it from a plant, extracted or obtained from a plant, a certain chemical or various chemicals. But the most famous is this molecule, again, switches off. And this is from the indigo plant. And it's an indigo dye. And it's a very, very dark blue. And who could afford to dye their clothes? Well, who's the richest people back in the Middle Ages? The king and his court, immediate court. And therefore, the color of the indigo dye, which is a very dark blue, is also called royal blue. Bet you never thought you learned that in my class. You did. All right, switch is still off, but I'd like to talk about an important area that's called the alkaloids. And the alkaloids are nitrogen compounds that are extracted, obtained from plant material. And some of the alkaloids have major physical effects on your body. And I mean major. So alkaloids are nitrogen-containing compounds from plants. Now, I'm going to talk about the next couple of slides, which still are click off, but in no way am I taking a moralistic stance. Now, remember, every bend in a line is a carbon, every end in a line is a carbon. Now, morphine, which became heavily used in World War II as a painkiller, especially on the battlefields of World War II, is this compound that Mother Nature created. And notice over here, I have a nitrogen with a CH3 on it, and it goes over this carbon and this carbon. So this is a tertiary amine. I've got an alcohol double bond, ether, benzene ring with a hydroxyl group phenol. Now, this is a very complex, what's called bicyclic ring in here. And I'm not going to get into it in this class. Actually, I know about them because my PhD thesis dealt with bicyclic rings and how to make them. But anyways, this is morphine. How does it kill pain? I have no idea. I'm an organic chemist, not a medical doctor. Now, if you look at morphine, I couldn't find a better structure. This hydroxyl group, alcohol in the benzene ring, I can make into an ether. And if you look here, we do. And this is the structure of codeine, which is a major painkiller. If you've ever had, it used to be Emperor 3, now it's Tylenol 3 with codeine. It does a good job killing pain. Also, if you ever had cough medicine, which they now make it hard to get because people are abusing it, elixir terpenhydrate with codeine. How do I know about that? When I was 10, I had asthmatic bronchitis, and I was coughing my lungs out literally one summer. It was awful. My father was a pharmacist. At that time, he owned his own drugstore. So I bought home a quart bottle for me to use of elixir terpenhydrate with codeine. And what is that? It's essentially 80 proof alcohol with codeine. You take a couple tablespoons of that when you're 8 years old. You don't care if you're coughing. You're feeling good. I was. But anyways, so the difference here is by changing this alcohol to an ether, which you know how to do, or I could show you, you have codeine. Now, an illegal drug is heroin. And what you can do is take morphine, or you can convert, and don't try this at home, it's legal and the feds know about it, convert codeine also into heroin. How do you do that? These two alcohols right here and here, you make into esters with acetic acid. Actually, not acetic acid, there's a better way. And this is heroin. And that's, people have been doing that. Again, these are illegal drugs. There are means, but I just thought I'd show it to you. And finally, another alkaloid. Notice right here on the right, there's a nitrogen. The line coming out is a methyl group. Again, this is a bicyclic ring. And here you have an ester, another ester, a benzene ring. And guess what? This is cocaine. This is a structure of cocaine. And how that gets people high, I have no idea. But here's the chemical structure. And think about it. At this point in your career, in my class, you understand some of the functional groups in there. Now, another drug that popped on the system about, I don't know, 10, 15 years ago is methamphetamine, otherwise known as crystal meth, because it's a white solid at room temperature. And this is a very simple little molecule. You got a methyl group on a nitrogen. Here you have these 1, 2 carbons plus this methyl group 3 to benzene ring. It's a secondary amine. How does this mess up your brain and make it do what methamphetamine or crystal meth does? I have no idea. And I see somebody have a question. Is it more stable now, Vivian? All right, everybody, can you see me?
Yes.
Can you hear me? Are you having a good time? I have to throw that in. You know me by now. All right, I don't know why it was unstable. I paid my bill. But anyways, actually, I got a new modem last end of last November, and things have been pretty good. The old modem was giving me problems. Anyways, this is methamphetamine. Now, another molecule that for a number of years in the rave clubs, which I'd never have been in one, but it was in the news, was this ecstasy. And it's very similar to methamphetamine. It has, the only difference is on the benzene ring, you have the acetal of formaldehyde. That's what the CH2 oxygens to the benzene ring. And it's made from, and I'm not going to show you how, from the derivative from the sassafras tree. And guess what? The government's long ago learned anybody who buys this, or it's even hard to buy it, is trying to make ecstasy. All right, some other naturally occurring nitrogen compounds, again, switches off. Silk is an amide, wool is an amide. Your hair and skin, we'll talk more about this when we get into proteins, are amides. And again, proteins are amides. So those are everywhere. And synthetic amides are things like nylon. And next chapter, I'll talk more about it. I won't put it on the board right now. I'm lazy. All right. Switch is partially on for this slide. And let's talk about heterocyclic compounds. First of all, you don't need to know, but they're the largest class of organic compounds. And this you should know. What is a heterocyclic compound? It's a ring that contains carbon atoms and other atoms. It contains carbon atoms and other atoms in a ring. And those other atoms could be oxygen or nitrogen. So you should know, what is a heterocyclic compound? It's a cyclic compound that contains carbon and other atoms, and those other atoms are either oxygen or nitrogen. Now, I won't ask, but many of them are aromatic, 2n+2 pi electrons. Now, I'm only going to ask you to learn switches on, click, see it's on, one heterocyclic compound, and that's pyridine. And this is the structure of pyridine. Notice it looks like benzene, except one of the carbons has been replaced by nitrogen. And it's aromatic, but it doesn't easily undergo electrophilic substitution reactions like benzene, but it is an amine. And it will undergo nucleophilic substitution, react with an alkyl halide. And in fact, remember my mouthwash? The quaternary ammonium salt, this is a tertiary amine, made from pyridine, is what keeps my gums nice and healthy. Now, this won't be on a test, but pyridine stinks. Awful. Imagine putting a dead fish in a plastic bag, leaving your backyard in the height of summer for 2 weeks and coming back and smelling it. Pyridine smells about the same, I bet. It's stinky. All right, switch is off. How many of you have heard that if you're young or if you're a woman who's pregnant, and even older people like me, you should have a lot of folic acid in your diet? and that keeps you healthy. How? Don't know, but medical science has proof. And some things like spinach and green leafy vegetables. Dr. White loves the spinach like Popeye. No, I don't eat it out of can though. And here's the structure of folic acid. Do not write it down. This won't be on a test, but it's a heterocyclic compound. Notice down here, you have a ring that's heterocyclic right here, nitrogen, 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 nitrogen in a ring with carbons. There are other functional groups, an alcohol, an amine, secondary amine, amide, carboxylic acid, which is why it's called folic acid. Now, how does this keep us healthy? I have no idea. But look at the amazing molecule Mother Nature has created. And also, it's amazing not only how complex it is, but in our bodies, it does good things, which is also amazing. Again, I'll never ask on a test what's folic acid. Now, switches off for the next couple slides, but it's important you just be exposed to some of this. Now, another heterocyclic compound is a 5-member ring, 1 nitrogen, 4 carbons, and it's aromatic. So you have the 2 double bonds and the non-bonding electrons that on the top are also in the pi orbital. So this is aromatic. This is called parole. Now, why am I talking about parole? Well, let's scroll down. Let me make this smaller. Now, if you put 4 parole rings together with a couple extra carbons, you have this macrocyclic compound. Macro means huge, big, and that's pretty huge. That's pretty big. And these are called porphyrins. And again, switches off, click. Now, where do you find porphyrins? Well, the heme and hemoglobin of your blood is a porphyrin. And chlorophyll, that allows photosynthesis. So plants can produce food, also convert carbon dioxide to oxygen, which is good for our planet, is also a porphyrin. Now, heme has an iron in the center that's associated, bonded to the nitrogens, and there are other proteins that are associated with this heme to make what's called hemoglobin. And this is a key chemical that's in your blood that allows your body to transport oxygen to where it's needed in your body. And now Dr. White's well beyond his level of expertise and knowledge of biology, and also remove carbon dioxide from your cells to get them to your lungs so you can breathe out and get rid of it. Now, instead of a iron, Fe, if you had magnesium and you had some stuff on the heme ring, you have chlorophyll. And that allows Mother Nature to take sunlight to make energy to do photosynthesis, which I won't get into in this class. Now, switch still off. This is called an indole, and it's also a heterocyclic ring. It's a fused ring, 6 and 5. Notice one of the carbons has been replaced by nitrogen. And it's in things like tryptophan, the key amino acid, and serotonin. Next, this is purine. Purine is a bicyclic fused ring, by 2 cycles or rings, a 6 and a 5. Some of the carbons have been replaced with nitrogens. And it's a key building block for, are you ready for this? Caffeine and theobromine. Bromine. I always say bromine, it's bromine. And that's the key ingredient in cocoa, which makes up chocolate. And it's also a key building block in your DNA and RNA. Switch is still off. Now, you don't have to write this down, but I don't know about you, but someone years ago gave me a coffee mug with that on there. caffeine. And this is a heterocyclic compound, and it's quite complex molecule. Now, interesting thing, if you look on the nitrogen between the two carbonyls, carbon bonded to oxygen, hold on. I'll have to catch it later. Bonded, hold on, one more. One more, maybe. Nope. Yep. Sorry about that. But anyways, if you look on the nitrogen between the two carbonyls in caffeine, it has a methyl group. Theobromine, which is the active ingredient in chocolate, cocoa, doesn't have a methyl group on that nitrogen, it has a hydrogen. Now, how many of you have ever heard people say, I'm a chocoholic? Luckily, Dr. White is not. I like chocolate. Actually, I like white chocolate, which is technically not a chocolate, but I can take it or leave it. It's not something I crave like, I don't know, good things, French fries, potato chip, stuff I shouldn't have. But you can get addicted to caffeine, and I was. At one time, I was drinking about 10 cups of tea a day, which was high in caffeine. When I cut back to 2 or 3, I felt it. And some people who get addicted to chocolate, because their body gets addicted to this molecule the same way it gets addicted to that. All right, we're done with this chapter. And like I said, we have finished up everything for amines, quaternary ammonium salts, amides, and their derivatives. And other than the little thing I just showed you about pyridine, what is a heterocyclic compound, we've covered everything for test number 3. Let's do Wednesday. Wednesday, I will go through the amines, amides, and quaternary ammonium salt or nitrogen derivative problem set. And we'll go through that. And that gives you a whole week to get ready for test number 3. Remember, do what you did for test number 2 if it worked well, and that's do the practice problems. And you can always go back and look at my videos. So, you know what time it is? It's new chapter time. Oh, I get to use this twice today. New chapter, new stuff time. Now, what I'm going to cover today and the rest of this week, other than the problem set on Wednesday, will be on test 4. I got to get that fixed someday. Test 4, not in test 3, but you should pay attention. Now, what I'm going to do first is talk about polymers. And I'm going to warn you, I could easily teach a 2-semester graduate level course in polymers. I've done a lot of work on that. My last patent, US patent, dealt with polymers, a type of polymer. So I know quite well. But in about an hour, hour and a half, I'm going to teach you everything you need to know about polymers, and we're afraid to ask. In other words, we're going to zoom through it real quick. It's not an in-depth coverage, but it still teaches you what is a polymer and some important polymers. All right, let's talk about polymers. And switches on, click. You should know what is a polymer. And a polymer is a macromolecule or macromolecules built by repetitive linking of smaller units called monomers. So a polymer is a big, which is what macromolecule means, built by repetitive linking of smaller units together called monomers. Now, I won't ask this on a test, but poly means many. And years ago, unfortunately, I think it was almost a year and a half ago, she passed away. There's a very nice lady who for many years was Dean of English at ECC, who I got to meet socially. Obviously, I don't teach English, never have, and don't think I ever will. And her name was Polly, and I did the stupid thing. Do you know your name means many in chemistry? And she gave me that look like, you know how many million times I heard that? I apologized immediately. But poly means many. Mer means unit. Now, that means many units. How many of you have ever been stuck at a train crossing where there's this huge freight train, lots and lots of cars going by, and you're stuck? Well, polymers like that, instead of having freight cars, and by the way, I'm doing a knuckle coupler because I'm a train enthusiast. Yes, I do model trains. I also do electronics. You can see a project I'm about ready to start, the materials for electronics. But anyways, think of, instead of box cars and a real long freight train, polymer is a huge molecule. Instead of box cars, the same groups of atoms connect together in a unit, keep on repeating lots and lots of time. And that's a polymer. Now, when we talk about polymers and switches on, there are different ways of classifying polymers. One is by the chemistry to make that polymer, and the other is by a key physical property. Now, when it comes to the two types of polymers based on, or types of polymers based on chemistry, the two are addition polymer and condensation polymer. Addition polymer, condensation polymer. Remember, everything I have on the screen here, you can find the slides on D2L. This one's in the lecture section, conveniently secretly titled Chapter 14, Synthetic Polymers. And I forgot to add the slide, so it's time to go to the whiteboard. All right, what is an addition polymer? An addition polymer is made with only one type of monomer. Think of a freight train and you saw a boxcar with the name Dr. White on it, not you'll ever see that. And the train only had boxcars that had my name on it. They were identical. That's what we mean by an addition polymer. An important thing about addition polymer would be that it's only one type of monomer. And what are examples? And you should know. And one of them is saran wrap. Or otherwise known as kitchen wrap or whatever they call it. I just know it, even though it's a specific company name, it's also been generic now, like Kleenex was for many years. You know, give me a Kleenex even if you only had puffs. But anyway, saran wrap is an example of an addition polymer. Another example are your PVC pipes. Those are examples of addition polymers. So if I ask on a test, give an example of addition polymer. There you go. Now, let's look at the other type of polymer, and that is a condensation. Again, this is classification by the chemistry used to make these polymers. And here, the key difference is I should have put or more, but usually it's just two. And monomers are the little group that are put together to make the polymer. Now, I forgot to say, in both these cases, you have close to 1 million, yes, 1 million, 500,000, 1 million monomers put together. That's one big molecule. Now, condensation polymer has 2 or more different types, and not only just 2, but types of monomers used to make that. And examples of that I should have put up here, saran wrap is called polyethylene. Not that I asked you on a test, but in case you wondered, example would be a plastic water bottle or pop bottle. I hope everybody knows H2O is water. You should. Now you do. And this is a polyester. If you own a nylon jacket, this is made with polymer nylon. So there are 2 types of polymers classification for polymers based on chemistry. You should know, ooh, I better be subtle. I like that. Dr. White can be very subtle. Know this. All right, addition polymer. It's a polymer made with only one type of monomer. Example, saran wrap, PVC, which is made from polyvinyl chloride. Actually, it's not polyvinyl, that's the name of the polymer. It's made from vinyl chloride, which I'll show you in a little while. I won't ask that, but in case you were wondering. And the other type is a condensation polymer made with more than one. Ooh, I forgot. Oh, bad, Dr. White. Guess what's another? I knew I was forgetting something, and finally, another one. Anything made of rubber, rubber is a polymer, and it's a addition polymer. And the monomer, which I'll show you later, is butadiene. Again, condensation polymer, where you have one or more different types of monomers as opposed to one type. An example of that would be my plastic water bottle. Or if you happen to go into the supermarket and buy a 2-liter bottle of pop or the smaller ones, those are also condensation polymers. And if you have anything made of nylon, like a nylon jacket, the nylon is a condensation polymer. Do I have time? I do. Back when I was in late high school, early college, the big trend was disco, which I hated. I didn't get into it. Thank God it died. And people were wearing these shirts and suits and sports jackets and pants made out of polyester. And you couldn't, it didn't allow air to go through and it didn't breathe. And I'll explain later when we get into carbohydrates about how fabric breathes. Can you hear my top? Oh, just inhale. No, that's not kind of what they mean by breathe. And wearing that, my mother said, oh, you need a new sports jacket and some shirts and dress pants, because we were going to certain weddings and things like that, family events, and we got all polyester. I felt like I was in a plastic bag and I'd just be sweating my brains out. And finally, when it got out of style, I just threw the thing out, all of it. I wouldn't even put it in, donate it to Goodwill or anything like that. I didn't want anybody else to suffer. And thank God that's gone. Thank you. All right, now, there are two ways of classifying polymers. One is by the chemistry. The other is by a key physical property. And the first type is called the thermoplastic. And you should know a thermoplastic, once formed, can be reheated to form a new shape. Like if you cut this bottle up into little pieces, I can reheat it and mold it into another bottle or other things, assuming I take the label off. And examples of this would be polyester bottles, saran wrap, if I can spell it right. And an interesting thing, there's no correlation between the chemistry of a polymer, how it was made, and whether it is thermoplastic, and the other one I'll tell you. So thermoplastic, once formed, can be reheated to form a new shape. And nylon is example, your plastic bottles, polyester, and polyethylene, which is saran wrap. So if I ask on test, give an example of a thermoplastic polymer, well, plastic bottles, saran wrap. Now, the other type is called thermoset. And thermoset, once formed, this cannot be reheated to form a new shape. And what that means is if you reheat it, it will burn, but it won't melt to allow you to make something new. And what's an example of this? Rubber, and I should have said rubber tires. Phenolic resins, which you don't know, but I do because I worked in this area. Unless you have metal buttons on, your buttons are mostly made of this material. And I'll talk more about urethanes, and this is for insulation, solid insulation, and seat cushion foam. And I could also say pillows too, which are either urethane or polyester foam. So again, Thermoplastic, once formed, can be reheated to form a new shape. Examples you should know, plastic bottles or saran wrap. Now, thermoset, once formed, cannot be reheated to form a new shape. An example of that would be rubber tires or phenolic resins, your buttons, and certain insulation. Now, if you've ever seen, and unfortunately I've seen it on news recently, not on fire, but where you see in a place of, how should I say this, violence going on in a country, you'll see people blocking the road with rubber tires. Why that? Well, if they set them on fire, they're not going to melt. They just keep on burning. And that's why they're good at blocking streets in a war-torn area. I guess that's the better way of putting it. Like if you've seen with what's happening in the Ukraine, unfortunately, what's happened to those brave people there. And every once in a while, you'll hear, every number of years, since car tires really can't be recycled into new tires like these can, into new bottles, what do you do with all these old tires? Well, you can retread them, sort of, but people don't do that. Well, you can cut them up and then spread them on playgrounds for soft sort of material underneath swings, but most of them are just put in a dump. And you'll have millions of tires in a dump. And once in a while, you'll hear where a car tire dump catches fire. How, I don't know. But once it starts, it's almost impossible to put out. And it takes sometimes years for it to burn out. Let's see something. And I can't find anything real quick. I thought I could find one. But if you look on YouTube, I'm sure they'll have that. Everything's on YouTube except for my high school graduation, I think. All right, let's get back. All right, switch is off, but addition polymers are formed from what's called free radical polymerization. I could do a whole 2-semester course on free radical chemistry. We're not even going to touch it in this class. But oh no, I just looked at my clock. And it's time for a break. Let's take a 5-minute break, come back at 1:55, and we'll continue with polymers. See you in 5. Time to get going. All right, we were talking about polymers. And we're talking about addition polymers, and they're made by what's called free radical polymerization. Switch will be off next couple of slides, but still interesting material. Now, what happens is you take a double bond, a molecule with a double bond. This is called a vinyl molecule, where you have something L. And polymer chemists use that letter L. I don't know why, but they do. And you have something that is called the radical initiator. And what the radical initiator is, converts this into a radical. And a radical is an atom, carbon atom, with one very reactive electron besides its other electrons. And you break the double bond, and this is a radical. And these are very reactive. And when you have a double bond, this attacks the double bond, the electrons, and you form a new radical. Again, switches off for this. And this can attack another double bond and can go on and on and on like the Energizer Bunny. I got to find a way to get product kickback. Anyways, and it forms this polymer. And remember this in a bracket, this repeats n times. And n here is on the order of 500,000 to a million and a half. That's large. Now let's look at some key monomers, switches off. When L is a hydrogen, this is called ethylene. You polymerize it to make polyethylene, otherwise known as saran wrap or kitchen wrap, I guess they call it. I just noticed the common name saran wrap. Now, when L is a methyl, same thing happens. This is called propylene is the common name, and you get polypropylene. How many of you have ever bought a flash drive electronics or something and got that bubble, plastic bubble on a card or something, and you try and pull it apart, you get a screwdriver, you know, it's really hard. Well, that polymer is polypropylene, and it's a lot sturdier by just putting that methyl group on there than polyethylene, a lot sturdier. Now, when L is a benzene ring, this is called styrene, again, switches off, and you make polystyrene. And if you make a foam out of that, how many of you ever seen the white insulated cups to put hot or cold things in? That's polystyrene. Or the super cheap, lightweight, that is also white coolers that you can buy in many places. That's polystyrene. And here are other ones. Now, when you have this molecule right here, second from the bottom, and L is a chlorine, you make polyvinyl chloride, which are those white pipes, at least in my house, underneath the sink. Now, when all L is a fluorine, the other carbons, hydrogens on the carbon are fluorine, you make Teflon, which is the non-stick pots and pans. So these play an important role in our daily life, switches off. Now, there's an important thing, switches on now. If you think about polymers, think of them as strings, but molecules, very long strings. And time for some Dr. White artwork. You are permitted to laugh your brains out. Let's say I had a polymer like this. Let's try this again. Each one of these lines is a polymer molecule. And they're all together like if you had a bunch of strings held together. And if you pull it this way, it's pretty strong when you grab the strings and pull it this way or this way. Now, if you have those strings in a bundle, but just held together by your hands, if somebody came by and pulled it this way, they'd fall apart very easily. Well, that was a problem with polymers early on. And about the 1800s, 1820, give or take 20 years plus or minus, they were trying, how do you make polymers stronger so they're useful? Well, it turns out there's a concept called cross-linking. And if I link this together like this by chemical bonds, now when I try and pull it this way, it's not going to fall apart. And this is called cross-linking. And cross-linking made a big difference in polymer technology. And it makes polymers more rigid and affects other physical properties, giving it better strength. Now, time for an interesting but sad story. How many of you have ever heard of Goodyear Rubber Company? Guess what? There's never been a Goodyear on the board of trustees or ownership of that company. Really? Well, back in the early 1800s, a lot of people were trying to figure out how can we make rubber useful. Rubber is a polymer. It has very natural rubber, very little cross-linking. And they were trying to find out how can we commercially make rubber that had use, could make them into things like tires or galoshes. Oh, I've used that word in years. Or raincoats. Back then, you'd have raincoats made of rubber. I mean, when I was in grade school, I had one. Anyways, how could you make it strong? Because natural rubber from the rubber tree is this gooey, soft mess. It's sort of semi-solid and not practical for him too much. Well, it turned out Goodyear found out. He was able to cross-link sulfur commercially, actually got a patent for it, by adding sulfur, and it's called vulcanization. How many of you have ever smelled rubber burn? It stinks. Natural rubber doesn't stink when it burns. The reason it stinks, car tires, like if they're on fire or if somebody lays a patch on a road and they burnt out, do a tire burnout, it's because it's really the sulfur burning. Now, Goodyear had one problem. He was an alcoholic. And these two very smart businessmen, I can't remember their names, approached Goodyear, and this is the early 1800s, and said, we'll give you a lot of money if you sell us the rights to your patent. And since everybody knows your name because of what you did, sell us the rights to use your name in our company, even though you won't be part of our company. And they gave him a lot of money. I don't know, back then 20, 30,000 was like giving someone millions. And because he was an alcoholic, that's what he did. Drank it all away, sad but true. But that's how rubber formed. And cross-linking has made a big difference in the physical properties of various polymers. All right, if you're reading the book, I'm skipping these sections. We talked about condensation polymers made with 2 or more different monomers. Each monomer has 2 or more different functional groups. And that's how it works. You have something like a diol, OL ending alcohol, 2 alcohols, or to make a diester. And the main functional groups, not the only ones, but the main ones in these type of polymers, which are condensation, are either ester linkages or amides. And some of the other ones, which are not, are urethanes, phenolic, polymers, which are made by reacting with phenol and formaldehyde. Also, epoxy, you can make polymers. Now, switch is totally off, but let me do a quick review. Polyester made with a reaction of a polycarboxylic acid or a carboxylic acid derivative with a polyol, poly-many-OL alcohol. And here we have a diacid, diol, and you form an ester here. Remember, you learned, and again, I promise no new general reactions. For test 3, hopefully you'll learn this reaction. Now, right here in this new molecule, here's our ester. Now, at this end, you have more alcohol, which can react with your carboxylic acid, diacid. And at this end, you have a carboxylic acid, which can react with more of your diol or polyol. And you can keep on building and building and building. And again, switches off here. Now, polyamides are made with either a diamine or polyamine and a derivative. Now, this is called an acid chloride, terephthalate chloride made from terephthalic acid and terephthalol. Yeah, my mouth doesn't want to work today. And this is an acid chloride, and it reacts just like a carboxylic acid, but much quicker. And if you have a carboxylic acid plus an amine, they'll form an amide. Now here, when you put a chlorine on the carbonyl instead of a hydroxyl group, you make this much more reactive. And this is how you make nylon. Now, a special type of nylon is when you react this diamine with this carboxylic acid diderivative, diacid chloride, you make this polymer, and it's a polyamide. Here's my amide. Again, switches off. And when N is 500,000 to a million, if you take enough of these and weave them together, the fabric, you can make layers, and we call that Kevlar. And because of the benzene rings, it makes this layers of that polymer very strong. And Kevlar, one of the uses is bulletproof vest for the police. Military, I don't think use Kevlar. They use body armor, which is even stronger than Kevlar, because those are ceramic plates, but it's a lot heavier than Kevlar. Now, here's an area I know a little about. I only have about 8 patents in this area, and that's polyurethane polymers. And this is made in reaction with an isocyanate, again, switches off, and a polyol. Now, what's an isocyanate? It's this functional group. And this is very, very reactive with water or with alcohols. Again, switches off. You take an isocyanate, react with an alcohol. You need a tertiary amine catalyst. And a hydrogen fell off. And this is called the urethane functional group. And these are very unreactive, therefore they're very stable. And urethane is very good molecule or polymer when you need stability. Now, the last one I'll talk about, by the way, I should point out, And we'll talk about this in a lab next week, not this week. Oops, that's not what I want. Urethanes, when you make a urethane foam that's solid, is a very good insulator. Next time you happen to walk by a refrigerator, look at how thick the walls are from the inside to the outside of the refrigerator, only about this thick. Go and look at pictures, if you've ever seen one, of a refrigerator from the 1950s, and the walls are about this thick. Why? Hold on 1 second. Maybe 2 seconds. Everybody see the old, that's sort of newish, but the walls here would be much that thicker. If you look at a new refrigerator, you look at the top, they're a lot thinner, much thinner. And that's because between the cold box and the outer surface, there's urethane foam. In the past, they used glass wool, like the Pink Panther stuff, like you see in walls and houses, even though walls and houses are now also coated with urethane. And that's the urethane. Now, the last one I just briefly like to talk about is if you react phenol with formaldehyde, this is sort of an aldo condensation. And it forms a polymer, which gets very hard, very hard. And this is used to be used to make many things until certain plastics replaced that. And the one thing about phenolic resins, they're very heat stable. And if you look at knobs of certain older ovens and stoves, they'll be made with phenolic resins. Also, my buttons are phenolic resins, and I worked with phenolic resins, can be a glue that form a polymer that holds sand together to make car engines and other things in foundry. It's also the glue used to hold wood together to make plywood and other composite wood products like that. The end. Like I said, I could do a whole 2-semester graduate level course, let alone undergrad, on polymers, but that's a quick taste. Hopefully you enjoyed it, of polymers and what they are. And you should remember certain things I just went over. All right, with that, I'm going to close this chapter out. And I get to do it again. It's new chapter time. And this new chapter, Dr. White looks like he's having a good time. I am, because I've worked in the industry that I'll be talking about for a number of years. In this area, I've worked in a couple of quite different areas of the chemical industry, which most chemists never do. But luck and new jobs that paid a lot of money, I jumped ship to other areas. And this new area, new chapter, are lipids and detergents. Now, I should warn you, this chapter, I'll teach you how you get your hands clean with soap. I'll also talk about some important things like how we make different chemicals that are used for your personal care products and shampoos and shampoo products and conditioners and other things. And don't get grossed out where they come from, because by the time you see them, think of them as chemicals. But this is going to be, ooh, and I'm going to get into something you never thought I'd get into. I mean, never thought I'd get into. I mean, never. I will, though. All right, let's talk about lipids. What are lipids? Those are constituents, things that come from chemicals that come from plants and animals. And they're characterized by their solubility property. Now, I'll never ask on the test what's a lipid. Switches off for this slide. But lipids are insoluble in water, but soluble in nonpolar, and I'll teach you about nonpolar this chapter, organic solvents like ether or hexane. So they're not soluble in water, but they are soluble in what we call nonpolar organic solvents, hexane or ether. I guess you could also put gasoline too, but don't try that at home, please. All right, switches on. There are two types of lipids. The first one is saponifiable lipid. And what's a saponifiable lipid? It can be categorized by, it can be hydrolyzed under alkaline conditions to yield the salts of fatty acids. And let me explain what this means. Saponifiable lipids undergo base, and alkaline means base, like sodium hydroxide. So what that means is, if you take a lipid, one type that's called saponifiable lipids, remember you learned about saponification of an ester. Well, you'll see where this got its name, saponifiable lipids, because when you treat that type of lipid with base and water, base hydrolysis, one of the things you get is carboxylate anions. Now, the other type is non-saponifiable lipids. And those do not react or undergo hydrolysis reactions in base solutions. So if you react the non-saponifiable lipid with, say, base and water, what you get is no reaction. Let me clean that up. Let me spell it right. Oh no, Dr. White's getting a brain freeze. I didn't even have any ice cream. I better be subtle. So, two types of lipids. Remember, lipids are molecules that come from plants and animals, not soluble in water, soluble in nonpolar organic solvents. And there are two types: saponifiable lipids, non-saponifiable. And a non-saponifiable lipid, when you treat it with base and water, base hydrolysis, it yields carboxylate anions. Non-saponifiable lipids, when you react it with sodium hydroxide and water, base hydrolysis, you get no reaction. So what's a saponifiable lipid? They're fats and oils. All fats and oils are saponifiable lipids. Now, what's a fat and oil? Well, it's a triester of glycerol, also called triglycerides. And a number of years ago, I went to a new doctor, and unfortunately he had to retire. He was great. And the person who I now go to at the same practice, she's also great. After I had my initial exam, general exam, and they took a blood test and all that, he calls me up and said, when can you come in? I need to talk to you. He said, there's some things you need to get under control, and one of them is your triglycerides. And he told me, and that's what I liked about him, and he wasn't being dramatic. He says, you're in the 95 percentile, that if you don't bring that down and get your blood pressure down and a few other things, you're not going to be alive in 5 years. That got my attention real quick. Guess what? I brought those down and I'm still alive. It's been more than 5 years, thank God. But anyways, this is fats and oils are saponifiable lipids. Now, what's the structure of a fat and oil? Why do we call it a triglyceride? Now, people who deal in fats and oils write it this way. And since I've worked in that, and that's called an oil chemist. Now, when people hear the term oil chemist, oh, you deal in oil from the ground, that black stuff? No, that's petroleum chemist. An oil chemist is someone who deals with fats and oils. And all fats and oils have this structure. It's a triester. And let's take a look at this here. What's an ester? Now I can draw it in the class for synthetic organic chemists. We draw our ester this way. Oil chemists draw it this way. All you've done is flipped it over and changed where the R and R prime is. And if we look here, I have ester number 1, R group oxygen carbonyl R. Ester number 2, same thing, except R can be different on this one, R prime, or it can be the same. And ester number 3. And again, R double prime can be the same as R prime and R, or it could be different. And all your fats and oils have that structure, period. And this area I worked in quite heavily for a number of years, fats and oils. Now, what's the difference between a fat and oil? Hold on, I forgot something from this slide. A fat is a triglyceride that's a solid or semi-solid at room temperature. You don't have to know what room temperature is, but in case you're wondering, it's 25 degrees C, and I think that's 77 Fahrenheit. And what's an oil? An oil is a triglyceride that's liquid at room temperature. So a fat is a triglyceride. What's a triglyceride? Oops, not on here. The one I just showed you. And all fats are solids at room or semi-solid room temperature. What's a semi-solid? Have you ever left butter out on the table after dinner and you take a knife or something and you push it in there, or if you're a little kid, you stick your finger in there and it goes down? What's this? Oh, come on, Neil, you should know better. 2 more rings. 1 more ring. Thank you. All right, sorry about that. But anyways, a triglyceride was semi-solid. You can push your finger in. Another example, you ever taken a knife or your finger, and you don't have to do this, and stuck it into a bottle of mayonnaise. It's sort of gushy, but it's sort of solid, but it's not a liquid, like if you put your finger into a glass or bowl of water, and it's a semi-solid. And if you've ever cooked bacon and left the liquid that's in the frying pan of fat sit there for a while, once it cools down to room temperature, guess what? It solidifies because it's a fat. Now, how many of you ever seen a bottle of olive oil or vegetable oil or corn oil? They're liquids. That's why they call them oils. So you should know a fat is a triglyceride that's a solid or semi-solid at room temperature. An oil is a triglyceride that's liquid at room temperature. Now, I promised no new reactions. Let's talk about reactions of fats or oils with acids or bases. See board. Well, I better get to the board. Now, I taught you, oops, wrong color. Right color. Now, for test number 3, you should know and I could have here HCl, which is what's in your stomach. But I showed you this and taught you it. So what if I wrote this backwards or rotated 180 degrees? And guess what? I'll change this order. You don't have to. You get the same thing. And why am I doing this? Let's look at any fat or oil triglyceride. And what makes the different fats and oils are what is the R group, or R prime, or R double prime, and I'll talk more about that later. So if I take this and react it with H plus, or I could have put HCl, which is H plus an acid, and water, this is 1, 2, 3 esters. And if we look at ester number 1 and think about this reaction, and here's my R prime, CH2, becomes an alcohol. This part here is my carboxylic acid here. And I'll draw it this way, backwards, which I should have up here too. And this is just the way fats and oil chemists, which I've been one, think. Now, let's look at ester number 2. Here's our R prime, here's our carboxylic acid part, but notice it's bonded to the CH2 above. Do you break carbon-carbon single bonds? No. So this becomes this alcohol, and the second carboxylic acid will be this. And finally, ester number 3. Here's my R prime, CH2. Notice it's bonded to the CHOH above and becomes an alcohol, this right here, plus my carboxylic acid. My R group here is called R double prime. So what do you get? You get this alcohol and these 3 carboxylic acids. Now this alcohol, which is really a triol, 3 hydroxyl groups, I taught you earlier, is called glycerin. And glycerin is used in many things in our society. And these are carboxylic acids because they come from fats. They're fatty carboxylic acids. But remember I told you how lazy organic chemists are? Fatty carboxylic acids. That's a lot to say. Why don't we just call them fatty acids? So if you take a triglyceride of fat or oil, or react it with acid and water, and what do you get? You get glycerin and fatty acids. Now, this turns out to be a very important reaction that you should know. We're going to room up there, so I'll put it underneath. And again, no new chemistry, just doing it in real life on a big molecule. Why? Because this is the way your body digests fats and oils. And in your stomach, you have water, you have acid, HCl, and you react that to make glycerin and fatty acids, which your body uses. Now, I worked for a company that did similar chemistry. I'll talk about it a little differently, where we took mainly fats, not oils, because it was cheaper, and we made glycerin and fatty acids to the tune of about 2 to 3 million pounds a week. I'll say that again, 2 to 3 million pounds a week of fat to make glycerin and fatty acids. And I'll talk more about it. Now, this is a reaction of fats or oils with acid and water, acid hydrolysis of fat or oil. Now let's look at remember, fat is a solid or something that's a solid or semi-solid at room temperature. Oil is a liquid, but they're all triglycerides. And the general form, and later in this chapter, I'll teach you specific fats and oils. But for now, let's just do a general. And we have the same triglyceride, 3 esters, and I'll write it backwards. And for test 3, you should know, if I take an ester, react it with sodium hydroxide and water, I will get back the alcohol I would have used to make that ester, plus the carboxylate anion of the carboxylic acid I would have used to make that ester. So if I take this triglyceride and react it with sodium. You can use other bases too, but for this, I'll stick to sodium hydroxide. Ester number 1, I'll get this alcohol. R right here is CH2 and still bonded to something. And then this part will give me this carboxylate anion. Next, ester number 2. And this will give you this alcohol plus this carboxylate anion of this carboxylic acid used to make that ester. And finally, ester number 3 will give you this alcohol plus this carboxylate anion. And again, you make glycerin. And carboxylate anions of fatty acids. And certain carboxylate anions from certain fats of certain fatty acids, we have a special name for. I'll teach you more specifically. We call those soaps. And this is how the original bar soap was made and still is made. They're carboxylate anions. Now, there's a slight difference in the reaction here, but I'll teach you that. So, if you have an ester, like you learned in carboxylic acid in their derivatives chapter, they'll be on test 3. You can do acid hydrolysis to get back the ester, the alcohol and the carboxylic acid you would have used to make that ester. And for fat or oil, here's the triglyceride, not 1, not 2, but 3 esters, and each one undergoes the same reaction, something you've already practiced, and you get glycerin and fatty acids. Now, if you do base hydrolysis of an ester of a fat or oil, which is a triglyceride, 3 esters, you get, here's our general reaction, base and water, you got an alcohol plus the carboxylate anion of the carboxylic acid you would have used to make that ester. Ester number 1 gives this alcohol plus this carboxylate anion. Ester number 2 gives this alcohol plus this carboxylate anion. And ester number 3 gives this alcohol plus this carboxylate anion. Now, let's talk about fatty acids. By the way, thumbs up, people. I haven't asked, does everybody see fatty acids on your screen now? Thank you. All right, fatty acids, I'll never ask you what they are in terms of the definition, but they're naturally occurring, means it comes from nature, carboxylic acids. They're always unbranched, straight chain. Mother Nature doesn't like branching, and they're always an even number of carbon atoms. And what I mean by even number, here you have a carboxylic acid, and this carbon plus the carbons in R in fatty acids are always even, always. And I call them long chain. They are. Fatty acids usually have from 12 to 26 carbons. The most prevalent is around 16 or 18. And I'll never ask you this stuff on a test, but it's something good to know. Now, and remember a long time ago, I talked about saturated hydrocarbons and unsaturated hydrocarbons. where saturated hydrocarbons are molecules that only have carbon and hydrogen atom, only carbon-carbon single bonds. Well, saturated fatty acids are molecules, fatty acids, carboxylic acids, 12 to 26 carbons that have only carbon-carbon single bonds. Now, I just noticed something. I didn't even realize it. See right here, Fa, that should be fatty acid. If you're in the industry like I have been for many years, that's the abbreviation. So you should know, switch is on now, click. What is a saturated fatty acid? And it's a fatty acid, which all the carbon chains, the R group, have carbon-carbon single bonds. Now, let's talk about an important example, and that's stearic acid. And you should know the structure of stearic acid. That's the common name. And this is, let me clean this up, do this a little better. You have a CH3, then 16 CH2s, carbonyl with hydroxyl group. Notice 16 plus 2 is 18 total carbons. And this is stearic acid. How do we know it's a saturated fatty acid? Because in this part right here, my R, they're only carbon-carbon single bonds. And this is a white solid at room temperature. Now, since I've worked in this industry, I can teach you about some stuff. If you look at a high quality candle, half the weight of that candle is stearic acid. Now, another product, which is made by a company which was bought out by another company, but for many decades they were a standalone company. Anybody ever hear of the company Benny Smith? That's a weird name, Benny Smith. Anybody? You know their product. It's, are you ready for this? Crayola crayons. Crayola crayons until Hallmark or someone bought them out. And I think they're still called the Benny Smith division. I don't know, I haven't bought a box of crayons in eons. Makes Crayola crayons. And half the weight of a crayon is stearic acid. The other half, like a candle, is paraffin wax. Both are non-hazardous. And how do I know that? Well, if you've ever heard of no parents whose children or know someone whose pets have eaten Crayola crayons, it doesn't harm them, other than it does have a colorful ending. Hint, hint, ooh. Anyways, when I worked for a company called Unichem Chemical, we were their supplier, Benny Smith, of stearic acid. And they had, at that time, they had a plant and their research and company headquarters in this right outside of Philadelphia, about half hour, I forgot what town it was in. And one day, the president of the company I worked for called me up and said, "You got to go tomorrow to Benny Smith. They're having a problem." And we were selling them millions of dollars of stearic acid. They're a very good customer. And so next morning I was on a plane to Philadelphia. The salesman for Benny Smith picked me up at the airport and took me to Benny Smith. And I got to see something amazing. I got to see him make Crayola crayons. Oh, it was high speed. The machinery they had was just phenomenal. And the problem, what happened was, the AK were coming out with 4 new colors, 4, 1, 2, 3, 4. And we may go a minute over, I'll still give you your 5 minutes. And on sitting a week or two or three in the box, just the very tip, the pigment that made that color, because stearic acid and paraffin are white, migrated away from the tip. Still, the rest of it was all right. But can you see a little kid getting a new box, wanting those new colors, it doesn't work because the tip is white. He goes crying, or she goes crying to their mother, and the mother gets upset and contacts Minnie Smith. Well, that was their problem, and I was called in to solve it. I can't tell you what I did because it's still a trade secret. If I told you, I'd have to, but no, I wouldn't. But anyways, and it was quite an interesting problem. One of the things I did see, which was awesome, the atrium to the corporate headquarters had these tall windows, and hanging from the ceiling were the winners of different contests Benny Smith, Crayola Crayon, would hold throughout the United States from kindergarten through senior year high school. And those were the winners. And those were drawings and artwork made with Crayola crayons. This was back in late 80s, early 90s. And even that, the work was beautiful. And with that, I went a whole 2 minutes over. Sorry, but I thought I'd finish the story. Come back at 2:52, and I'll see you in 5 minutes. oh no, I'm running a whole minute late. I'm late for an important date. Time to get started again. Sorry about that. And everybody back? One more quick story. I was working in McCook, and at the time I knew quite well about stearic acid, and stearic acid is not hazardous. And I forgot what metro train goes through Western Springs, but right near the train station, someone found on the tracks this big pile of white powder, and nearby there were these bags labeled stearic acid. And the funniest thing, they shut down the whole train system. Dangerous chemical, not. And I don't know how many hundred thousands of people were inconvenienced because it took them a couple hours for someone to tell them, guess what? That's not a hazardous chemical. It pays to know your chemicals. All right, so stearic acid has this structure, and you should know it. If on a test I ask you to draw the structure of stearic acid, that's what you draw. Now, this is a saturated fatty acid, which means it has only carbon-carbon single bonds in the R group. Now, there's also a type of fatty acids called monounsaturated fatty acid. Now, if you remember a long time ago, saturated hydrocarbons, molecules with a carbon, at least one carbon-carbon double bond or triple bond. Guess what? First of all, Mother Nature never did triple bonds. Never, never, never. It's never been found. Organic chemists did, but not Mother Nature. So mono, meaning one, unsaturated fatty acid, you should know, is a fatty acid as having a carbon chain in which at least one, or in the monounsaturated, one carbon-carbon double bond is present. So a monounsaturated fatty acid is a carboxylic acid that has at least a one carbon-carbon double bond. And the one I'd like you to know is oleic acid. And oleic acid, seaboard, well, right underneath this, has the following structure. And notice this also has 18 carbons. 8 plus 8 plus 2, 14. Let's see, 16 plus 2 is 18. And this is, remember, carboxylic acids are always number one. At carbon 9, and we call that C9, there's a double bond. Now, this double bond can be cis or trans, and I'll talk more about that in a while, if not today, then Wednesday. So oleic acid is a carboxylic acid, a fatty acid, comes from fats and oils, and this R group has one double bond. And if I ask you, draw the structure of oleic acid, remember this is for test number 4, not test number 3, there's the structure. Again, CH3, 7 CH2s, we put it in bracket because that repeats, double bond, 7 more in the carboxylic acid. And this is oleic acid. Now, you can also have polyunsaturated fatty acids, which I'm not going to really talk about. And those have more than one double bond, 2 or more. And I'm not going to talk about these. Now, let's go back and look at oleic and stearic acid. In many of the products you buy, and now we're getting into the good stuff. If you look at a label and you see something stearate or something oleate, especially personal care, hand lotions, I'll have to bring Wednesday, I'll have a show and tell, Dr. White's show and tell. It's going to be fun. Well, anyways, if you look at the label like hand cream, you'll see things like a name at the end of that name of the chemical, the ingredient, you'll see oleate and stearate. And those are esters. Remember, AT ending is either a carboxylate anion or an ester, but those are esters mostly, there are exceptions, but mostly from oleic and stearic acid. And those are used to make a lot of things in our daily life. And they all come from fats and oils. Now, as I said, in stearic acid, oleic acid, monounsaturated, this time in the semester, you got to be patient because I'm writing out big molecules. This double bond can be cis or trans. And just to remind you, in a alkene double bond, when both hydrogens are on the same side of the plane, this is called cis. And this, when they're on opposite sides of the plane of the double bond, that's called trans. How many of you have heard of trans fats are bad for you, cis fats are better? As my doctor always reminds me, but you got to take both in moderation because even too much, even cis fats is not good for you. Nobody's heard of that? How about give me a thumbs up if you heard about cis and trans fats? All right, at least one person has. Where does that come from? Now, remember, say for oleic acid, this is the R group that's in the fat or oil that you get when you do acid hydrolysis. So if this R group is either this one, or it could be R prime or this one, if this is cis, you'll have a cis fat. Or if this is trans, you'll have a trans fat. So that's how they get the name cis or trans fat, or oil too, but usually, and that's because of this double bond in the R group are the hydrogens on the same side, it's on the other side, or opposite side of the plane of the double bond. Now, a number of years ago, I was going to teach at ECC. I got off, or I was getting off at McLean I was at 19. And next to me, once I got onto McLean, was this huge semi. And on the side of it was a picture of something very dangerous for Dr. White, Lay's potato chips. And this is when medical science was really pushing hard. Trans fats are bad for you. On the side of the truck, it had the picture of the upper part of a bag of Lay's potato chips, which was dangerous for me. They just evaporate like that. Open a bag and around me, and even a big bag, and within an hour or two, it's gone. I only buy those a couple times a year on my birthday and around the holidays. They're just too dangerous. But anyways, and back then, the upper right-hand corner, which was also at that time on the bag of potato chips, when if you went and bought them, said 0 trans fat. I looked at that and I smiled, I started laughing. I said, I bet I'm the only one around this truck right now who means that means a double bond. The hydrogens trans are on the opposite, and the cis one, they're on the same side. And now you know too. Why does that make a difference? One's healthier than the other? I have no idea. Medical science has found that, and I believe them. All right. Now, part of the slide switches on, part of it's off. Now, fats and oils are very important in the chemical industry and obviously in food industry, cooking with or making things with. When you have beef fat, that's called tallow. And you should know this. Now, I'll put this on a pig's fat. Now, I have BFT. This is a special grade of tallow. It's called bleachable fancy tallow. Since I worked in this industry and at the company I worked at, because I was the laboratory manager in charge of both quality control and all research, part of my job was to work with the purchasing agent to make sure he was buying good stuff, not garbage, which I had to educate him. And he'd always ask me, can I buy this or that? I'd have to have it analyzed if they were buying a lot. What's a lot? Maybe 10 million pounds, and which is a lot of money. So the other type that you should know, pig's fat, which you know is lard, but there are 2 types, white and yellow grease. And the white grease is a slightly purer than the yellow grease. And this has come from pig's fat. And the company I work for, each week, we'd buy and use 2 to 3 million pounds a week of either tallow or yellow or white grease. For most of what we did, yellow and white grease would be sufficed. And it's cheaper. What do I mean by cheaper? Depending on various factors going on when you're buying it, like, are there any problems with disease with beef or with pigs, things like that, how much are being slaughtered and processed for meat, and the fats rendered into yellow grease, white grease, or tallow would indicate the price. Now, usually yellow grease and white grease is about 3 or 4 or 5 cents a pound cheaper than tallow. Well, if you're buying 100 million pounds or more a year, guess what? 2 or 3 cents, that's a couple $100,000. So whenever we could, we would try and get yellow grease, white grease. Now, other ones you already know about: coconut oil, soybean oil, corn oil, olive oil. Those you all cook with, but the industry I worked with in the chemical, these are more expensive, much more than tallow and white grease and yellow grease, so we don't use them. Now, there's an interesting oil called rapeseed oil. That's an interesting name. And turns out most of the world uses rapeseed oil. is some very inexpensive seed oil that comes from seeds from the rapeseed plant. I don't know how I got that name, but that's what it's called. And in the United States, if you go to your supermarket, you're not going to find rapeseed oil. No, no, no. Not even a ethnic one. Why not? If you go to, especially since it's very inexpensive cooking oil, you go to an underdeveloped nation in Africa or other countries in the world that are not at the same level economic, they're citizens of the United States, most of the people are using rapeseed oil, and you can buy it in a jug or whatever they sell it at as rapeseed oil. But for some reason, when they tried to do that, the American housewife said, I'm not going to buy this rapeseed oil. Well, where's one of the places rapeseed oil is made? Canada. It just grows real good there. Don't ask me why, and why don't we grow more? Because we grow a lot of soybeans in the United States, which we also get soybean oil and other things from. But the people up in Canada, somebody very smart at this one, what would be the right term, professional organization of rapeseed oil producers. They have an organization up there. Someone in marketing sales came up with a great idea. Be great if we could sell our rapeseed oil to the Americans, because it's a huge market, and it is. So whoever it is came up with the idea, well, if it's not acceptable to use rapeseed oil, and it's oil that comes from Canada, why don't we call it canola oil? In the United States, you buy canola oil, you can get it everywhere. And that's really everywhere else in the world, rapeseed oil, same thing. Let's see something. If you look on your screen right now, you can see all these different big name companies sell canola oil. I don't see rapeseed oil anywhere here because you can't find it. For whatever reason, Americans, and especially the American housewife, was totally turned off by the name. Everywhere else in the world, it's acceptable, but not here. Interesting sidelight. All right, let's go through it again. Let me actually put it on a separate slide. If on a test, I would ask, what's tallow? You should know it's beef fat. What's yellow grease or white grease? And those are two different types of pig's fat. Now, one of the interesting things is tallow and yellow grease and white grease are very important chemicals in the United States and throughout the world. In fact, one time I was asked by the CEO, the president of a company in the United States I worked for, then it was called Unichem Chemicals, since been sold to someone else, that helped with our purchasing agent to ship, I think it was 2 million pounds of tallow from New York to Rotterdam, make sure it gets there in good condition. And we buy 2 million pounds, that's good too. And I did. Now, tallow and yellow grease and white grease are so important that various contracts for chemicals made down the road from those, many steps down the road, those contracts are based on the price of formula of tallow and yellow grease, white grease. Price of tallow goes up, those chemicals go up. Goes down, the prices of the company who are buying those chemicals pay less. And it's so important. Are you ready for this? If you know where to look, I do, you can find a weekly quote for the price per pound of those chemicals. Where are they located? One place every Friday in the Wall Street Journal. Yes, in the Wall Street Journal, they have price of yellow grease, white grease, and tallow. Now, there's another magazine that when I worked for this company, I got, and other people did too. We had a monster subscription, and that was called Chemical Marketing Reporter. And once a week, I think it was Friday also, they would also have the price of tallow, yellow grease, and white grease. That's how important it was. Whoops, too big. Now, in fatty acid nomenclature, nobody uses IUPAC names. They use common names. Stearic is really, the IUPAC would be hexadecanoic acid. Nobody calls that. They call it stearic. And here are a couple of saturated, and the only one I'm asking you to learn is stearic. But if you have 12 carbons, the carbonyl carbon, remember here, COOH is carbonyl with hydroxyl group. That plus 10 plus 1 is 12. That's called lauric acid. Myristic is 14. That's not that common. Lauric is. Palmitic is common. Stearic is. Next one, I don't even know how to pronounce that. I never worked with that. Now, these are all saturated, only carbon-carbon single bonds. And next time you happen to be, say, in your bathroom, pick up something like a hand lotion or something. And if you see palmitate, stearate, or laurate, those are molecules that were made from lauric acid, palmitic acid, or stearic acid. Now, unsaturated would be oleic acid, which I already, now here they have it's a cis double bond, but guess what? It can be a trans. And linoleic, 2 double bonds, linolenic, 3. They have all cis. No, you can have trans. Whoever made up this chart in this book, which is a good book, but this chapter shows they never worked in the industry like Dr. White did, me. And if you look and you see mainly something like oleate, you know, is something, an ester or carboxylate anion that came from oleic acid, which came from usually beef fat or pig's fat or yellow grease, white grease. Now, switch was off on this slide, switch is off on the next slide. This slide, I'd show you something interesting. If you look at animal fats, and butter is about 28% unsaturated fatty acids, which is the R groups on the triglyceride, and the remainder are these saturated. And if you've listened to medical science over the last number of years, they've talked about unsaturated fats and oils are much better for you health-wise, meaning clogging up your arteries, than saturated fats and oils, which is why butter too much is not good for you. And if you look at lard, which is yellow grease, white grease, I always laugh when I see this beef tallow. There's no other type of tallow. Beef is tallow, beef fat. But anyways, if you notice here, it's a little more unsaturated. this one, they say 51 for lard. No, it's more, how should I say this? About 50. And tallow is about closer to 52. So there's equal amount of saturated fats, fatty acids and unsaturated, which means the R group on the triglyceride has an equal amount of saturated and unsaturated R groups. And again, the more saturated fatty acids or fats you use, or more saturation present, the worse it is for your health. Now, what's one of the most commonly pushed, this is a healthier oil, and that is olive oil. And if we look at olive oil, again, switch is still off, it's almost 90% unsaturated. The higher the unsaturation, the better it is. And compared to about 50% for yellow grease, white grease, pig's fat, or this is really closer to 50% tallow, beef fat, this is healthier because it's higher polyunsaturated. Same thing if we look at corn oil or peanut oil or any vegetable oil is highly unsaturated. And the fatty acids you get from hydrolysis, how you break it down in your stomach, is also highly unsaturated and more healthier for you, even though the overall fats and oils you should cut down on. All right, let's go back into real world. And let me just check something. All right. Now, since I've worked in this industry, the first time I started teaching this long ago, I was thinking, I know fats and oils real good, and I do, and I still do, and I consult in that area. How can I teach the student and give the student a real good feel for dealing with real fats and oils, not just R prime, R double prime, R triple prime? I came up with the following idea that I've been using ever since. Now I look better. And let's go to my whiteboard. I would like, whoops, gotta get you on there first. I would like you to use the following. And for tallow, yellow grease, white grease, remember tallow is beef fat. And yellow grease, white grease is pig's fat. And what is that? Let's look at this triglyceride. Now I'm going to use an abbreviation for this structure. And notice I have R sub S. And when you hydrolyze this part here would give you stearic acid. R sub O, this part here, would give you oleic acid. Now, in real life, there's about a 50-50 mixture of saturated and unsaturated fatty acids coming from the hydrolysis, acid hydrolysis of any of those tallow, yellow grease, white grease. How do I know? Well, I worked in that industry for many years, and it's true. Isn't that nice? I don't lie to you. It's true. But anyways, this is the structure you should use for tallow, white grease, or yellow grease if I'm going to have you do some chemistry. Now, if I ask you, and let me just give an example, R sub S, what I'm really meaning, I need more, I have enough room. This part of stearic acid is what I mean by R sub S, R sub O, and this is easier. Remember, organic chemists are lazy. Why are we lazy? This is a 7. And this is what I mean by R sub O. And this is a very good approximation. Now, unfortunately, how do you get 50-50 when you have 3 things? You can't. So just for our use in this class, what I have is 2 of the R sub S and 1 of the R sub O. You could have 2 R sub O, R sub S. It gives you the same thing, but I thought I'd do it this way. Why? SOS. That's my personal joke. Save our ship. All right. So this is the structure I would like you to use when we react either yellow grease, white grease, which is pig's fat, or tallow. Do I have time? Oh, I do. Time for a quick story. When I worked at this company, Unichem Chemicals, which is still, the plant and everything is still 47th Racine, right next to the stockyards, which is where originally they got their fat and oil, because in the stockyards they were killing cattle and pigs, and the companies like Armour were right there processing those cattle and pigs, and the fat they would sell to companies right around there. Well, the site the company I worked for was on originally was owned by the Darling Brothers rendering company. And we bought the company I worked for, Unichem, their fatty acid division that made fatty acids from fats and oils. And we also made esters later on. But anyways, on that site was a rendering plant. And one of the smells, and most chemical plants, you get used to the smells. A rendering plant, you never do. Luckily, my office was upwind, so the wind didn't push the odor at mine, blew it away. By the way, this was a couple of blocks away from the old White Sox Park, which is why that area sometimes smelled, especially when the stockyards were open. I went in that area, IIT, and it did smell sometimes. Well, anyways, when we bought it, there was an agreement that within 10 years, Darling would close the rendering plant. What do I mean by rendering? Have you ever made bacon or hamburgers, and after you take it out of the pan, frying pan, there's a liquid in there, the fat, and you've rendered out, taken out the fat. And Darling, what they did would be they would get fat from butchers, or if an animal died before it was slaughtered properly, they couldn't use it to sell the meat from. That whole thing just got shipped to Darling, and they had the equipment in these huge tanks that would heat it up to get the fat out. Before that, if it was live like that, not live, but still had blood in it, they'd capture the blood and they sold that. And then the bones and everything they sold to someone too. And we bought the fat from there. And funny story that happened to me is I was a senior manager, not in the regular parking lot, but I could drive into the plant area. And they had a special area that had overhang and protect your car from the weather. I parked there because I had I had my own parking space that had my name on and everything. But anyways, I would get there early. That company let me start early. And if I didn't have any meetings, I could leave early, 8 or 9 hours later. What's early? I'd get there about 6 a.m., which meant I beat all the traffic on the highways. And coming home, if I got there at 6, I could leave by 3:30 and again miss rush hour, a good part of it, which was nice. So I get there, it's no dead of winter, 6 a.m. and guard opens it up. He knew me, opened up the gate, and I'm driving in. And this was a pretty big site that had its own streets. And right in the middle of the street was a dead cow on its back with its legs sticking up, frozen like a popsicle. Not the best way to start your morning. So I park, go to my office, and because of part of my job in waste control on that site, responsibility for it, I had to deal with the plant manager at the Darling plant. I called him up and I said, Bill, we got a problem. He said, what's wrong? I said, I was driving in, there's a dead cow on our plant, on this area of the street in the plant. So, oh, it must have fallen off the truck. I'll get someone with a forklift to take care of it. And I said, thank you. Not a quite unique way to start your morning. Oh, I should point out, well, I'll get to it another day. Now, let's talk about hydrolysis. And I'll talk about first with acid and then with steam, very hot water. Oh, sorry, I got shut down, open up again. I forgot to do it during the break, sorry. We're back in business. All right. I use HCl because that's the H plus in your stomach, and water, and what would be the products. Well, if you see tallow or anything else, let's use this designation. This triglyceride. And it'd be the same if I asked for yellow grease or white grease. Remember my little joke, SOS. And we're reacting with HCl, which is H plus, and water. Now, as I showed you earlier, no new reaction. I'm just writing it backwards because that's how oil chemists do that. You take an ester, react with acid and water. Remember, this is happening in your stomach. You get back the alcohol plus the carboxylic acid. And I'll write it this way, the way fats and oil chemists do, or oil chemists. So if we look at ester 1, 2, and 3, ester 1, I'll get this alcohol. You've seen this before, but now our here is stearic acid. Now, ester number 2, I'll get this alcohol. And notice the R group here is R sub O, so I'll get oleic acid. And the final ester, I will get this alcohol. And this group will give me stearic acid again. Now, on my test, I never ask you to balance an equation. What do I ask? Give the organic product or products. And therefore, you'll get glycerin, stearic acid. Now, if you want to, you can put a 2 there, stearic acid and oleic acid. And that's what would happen in your stomach if you have acid hydrolysis of tallow, white grease, or yellow grease. You get glycerin, stearic acid, oleic acid. Like I said, we did that, but not this exact reaction. Now, something you should have learned in general chemistry. How do you make a reaction go quicker? One way is use a catalyst. And we do, that's why we added the acid. A catalyst makes a reaction go quicker. Now, what's another way to make a reaction go quicker? Increase the reaction temperature. There's a rule of thumb, it's on this thumb, see? Oh, that was bad, Joe. Anyways, for every 10 degrees C, you increase the reaction temperature for most, not all, reactions, the reaction rate doubles, goes a lot faster. And in industry, time is money. The quicker you can make something, the more money you can make, because the more time is in the reactor, the more it costs. Well, what's higher temperature? Well, if we look at let me get to where we were going. In order to increase the hydrolysis without using acid or base, I can use very hot water. Hot means a higher temperature than what we did with acid. And what's the definition of hot water? Real hot? Steam. And in a chemical plant, high pressure steam is dangerously hot. It can kill you if you're not careful. You get hit with that. And so let's look at the following. In this case, let's start with tallow again. And now what's steam? Hot water. And let's remind you, it's the same as acid hydrolysis, except now we have steam. So it's the temperature, not the acid, that catalyzes it. And you get back the alcohol plus the carboxylic acid that you would use to make that ester. Well, tallow or white grease, yellow grease, isn't it nice? You already know these general reactions. We have our 3 esters, and if we react it with steam, and just to remind you, that's hot water ester number 1, I'll get this alcohol plus, notice here, I'll get stearic acid, which I'll write this way. Ours the best. Second ester, I'll get this alcohol. Remember, that's this going to this, which is that, plus what's this? Oleic acid. And finally, the last alcohol, last ester, I'll get the last alcohol, and I get glycerin. And again, here's this. This is an S. I'll get stearic acid again. If you want, you can put a 2 there. You don't have to. So again, you get glycerin, oleic acid, and stearic acid. And if I look at the clock, I'm just about out of time. Don't forget, continue handing in your labs. One's due this Wednesday. Also, this Wednesday, I'll go through the amines problem set. And don't forget, tonight from 5 to 6:15, I have my office hour. If you have any problems, stop by on Zoom and ask any questions. Remember, in my class, there's no such thing as a dumb question. With that, I'm done. Gang gesund. Goodbye now. I'll see you on Wednesday, unless you come to my office hour tonight. Gang gesund. Bye.